So I prepared what I think, in my view, is the issues that we have ahead of us to develop fusion as an energy source, and then what we can learn from ITER and other experiments, and what we need to have a specific infrastructure. So the first thing is, I think that either this is something that ITER will do, and Spark can do it, and maybe even faster, which is to show that we can actually create a plasma that is self-heated and control it over time scales which are relevant to the process, which are actually, in the case of ITER, are time scales of several hundreds of seconds. In the case of Spark, are time scales of the order of 10 seconds, because the machine is smaller. Now, so this part, I think, is something which is not so far away in time, and as I said, to me, this is very important, because this is the first time that we will see if our predictions materialize or not. If they materialize, then they will have a very good basis to optimize fusion reactors. If they do not, then we have to be careful, because the models that we are using to design and predict actually do not work, and it's not the first time that this has happened in fusion. Now, one thing that we have to do is also to handle the fluxes to the wall of the reactor, particularly the fluxes, not the neutron fluxes. The neutron fluxes is something with materials, but in terms of power fluxes is in a way less demanding, is the fluxes that the hot gas deposits on the wall, and this is because it goes to very small areas. This is something that we expect to do in ITER, because if not, we cannot run these discharges. In Spark, this is less clear, because they can use other tricks, let's say, like strike point sweeping that was developed at JET in the 90s to avoid this, to handle this issue. Of course, they will try, but for us it's essential. Now, whether this is enough for a reactor or not remains to be seen, because this is one of the things that we have to show. In principle, ITER has the capability to test some of the exhaust, what we call exhaust solutions, but not all of them. Some of them may require specific facilities, like things like they can try in Spark or Arc, etc. The others, I think, can be well done in ITER, because the machine has enough power to demonstrate. So there we will probably know if we have a scenario that the plasma is self-heated and doesn't destroy the walls of the reactor. And to me, these are the two large scientific challenges, whether what we predict will happen, and second, if we can keep it for long enough. And I think this is something within the time scale of the next generation of reactors. The experimental reactors will demonstrate this. If this doesn't work, you cannot go ahead. You will never build a power plant without this. That is why scientifically is very, very important. But this has nothing to do with the technology, it's pure science. Then we have, for control, one thing which is very important that you have to realize is that controlling this we have a lot of actuators and a lot of sensors. So in ITER, we have actually 60 diagnostics, and we measure more than 100 properties of the gas and of the neutrons. And this is because it's experimental reactor. This can never be made a power plant. It is very complicated. So actually, the next step that we have to learn, this is the step of the control. Once we have got fusion, is how we do this in a practical ways. This is a bit like, you can drive a Formula 1 car and you can go very fast, but you will never use it to go on summer holidays, because you will probably not reach the beach. It will break it on the way. So the experimental reactors are not power plants. They have all the tools to make fusion, but once we get there, we have to simplify. And actually, one of the things that we want to do in ITER after we got fusion is to see how many of these things we can switch off. We can actually have fewer and fewer sensors and fewer actuators. And of course, once you have learned, you know what is essential and what is not. And there, one of the things which I see, and this was mentioned today, I think artificial intelligence may open new ways. Because once you have the plasma, you have the measurements, and you know how to control, this can tell you this can help you to identify what is the minimum set of actuators. This is something that I think has a lot of promise to simplify the way you operate and potentially design a reactor. And just to give an example, for instance, in ITER we have 3 heating systems. So we want to get the gas temperature to high temperature. We need to get the gas 100, 200 million degrees C. So we have systems which are based on heating the electrons of the gas, or heating the ions of the gas, or heating the electrons and the ions. And we have enough flexibility to try one of them. So ideally, what we would like to do in a reactor, or many people think what we would like to do in a reactor, are use RF systems only because they are much simpler, you don't have accelerators. So in ITER, we have the capability to test one of these systems. If we can do it, it means that instead of having to design reactors with multiple heating schemes, which is very complicated and very expensive, you could choose one. And then, of course, once you choose one, you go into series production, because this is the system you are going to use in power plants. You don't need to maintain 4 development lines. So this, to me, I think the issue of control, I see also a very important step. And then we have the issue of the technology. And as I said, I think that ITER and next step reactors that have long pulses, experimental, will actually be able to handle the issues related to the plasma and to the neutrons, because the neutron fluxes are of the right order. They will demonstrate how you operate a superconducting magnet on long time scales, and also the tritium management that we discussed today. So, for instance, one of the things that we have done in the latest ITER design, in order to reduce the inventory of tritium, is to modify the tritium plant so that it can work in the same way as the one of a fusion reactor, with the hope of advancing this. Now, the problem, what we will not do in ITER, is the issue, and this was discussed today, of the impiled tritium production. ITER will not provide the tritium, we'll just have a proof of principle, and we'll also do a proof of principle that you can generate hot fluids to do electricity. But this is something that you cannot demonstrate, and for this you need some specific facility, such as, for instance, was discussed this week, a neutron facility, because ITER will not do this, it doesn't have enough fluence. The total fluence of ITER, if it could be operating as a fusion reactor, would be 6 months. So this, we cannot demonstrate all the aspects related to high fluence. So we don't demonstrate material degradation, large-scale triton breeding, integration into the electricity network, etc. So this requires different type of experiments. So for me, this is the challenge is, I would say, the challenge that I see in the technology side, I see more on the breeding blanket and things related to material degradation. The rest, I think, to some degree, between devices that are now being built and ITER, will probably be assessed on the technology side. We will have magnets that operate at high current, that we will know how to control, that will work at relative and neutron fluxes. But all this bottom part in orange here, this we will not know.
Thank you. Thank you for your...
Thank you.
for your